Okay, so these are questions number 40 and number 41 of the electric fields and the capacitors homework booklet. So in question number 40 we have a diagram here and it shows the field lines and the equipotential lines around an isolated positive point charge. So it's a radial field, as we can see, because the field lines are all pointing outwards, and the concentric circles around here, these are forming our equipotential lines. And we're looking for one of these four statements to be incorrect. So we've got four statements and they all concern the work done when we move a small charge in this field, and we're looking for the one that's wrong. So as a really quick reminder, when we're looking at the work done of moving a small charge inside this field, if we're moving a charge of Q, so this Q here, through a potential difference of delta V, then the work done is simply those two numbers multiplied together. So we're going to have a look at these four different situations. So case A, when this charge is moved from either P to Q or S to R, the work done is the same in each case. Well, if we move from P to Q, we have a potential difference of moving from this equipotential to this equipotential. So we've got Q multiplied by the potential difference from here to here. S to R, we've got the same charge Q, and because this equipotential and this equipotential are the same, the potential difference will be the same. So the work done moving from P to Q and the work done moving from S to R is exactly the same. So that one's correct. So our answer is an A. When it's moved from Q to R, no work is done. Well, Q to R is on exactly the same equipotential surface. So the potential at Q and the potential at R are equal to each other. So delta V, the difference between the potential here and here, is 0. So Q times 0 means that the work done is 0. So B, when it's moved from Q to R, no work is done because the work is 0, so that is correct. When we move around the path P, Q, R, S, then the overall work done is 0. So we're going P to Q, Q to R, R to S. So we're taking that path there. Well, P to Q means that the electric field does some work because this is a positive charge. Our test charge that we always think about is positive. So moving from here to here means that we get some work out of the field. When we move from here to here, as we've just seen, no work's done. And then when we move from here to here, we have to put some work in. And so therefore, when we get work out and then we get the same amount of work in, you've basically got a positive value and a negative value, and then when you add those two together you go back to 0 again. So when we move around P, Q, R, S, the overall work done is 0, so that's correct. So A, B, C are all right, which basically means that D has to be wrong. We can check that it's wrong. Again, we're looking at the path P, Q, R, S, P, Q, R and S, and they're saying that the overall work done is twice the work done moving from P to Q. Well, that's obviously not right, because moving from P to Q is minus moving from R to S. So if you add those two together, you get 0. You don't get twice the work done moving from P to Q, so D is obviously wrong. So question number 41. The question number 41 is a calculation question. So we've got, we're now looking at capacitor, and we've got an uncharged 4.7 nanofarad capacitor, and we connect it to a 1.5 volt supply where it becomes fully charged. And we want to know how many electrons are transferred to the negative plate of the capacitor during this charging process. So as it charges up, the potential difference across our capacitor eventually gets to 1.5 volts. So when it's fully charged, the potential difference across it is 1.5 volts, and we know the capacitance. So if we look at this equation here, this is our standard equation actually for the definition of the capacitance. The charge on one of the plates is equal to the capacitance of the capacitor multiplied by the potential difference across the capacitor, and we know both of those numbers. So that there is our capacitance. We multiply it by 1.5, which is our potential difference, gives us 7.05 times 10 to the minus 9 coulombs. So that's the charge on one of the plates, and if we put a minus sign in front of it, that would be the charge of the negative plate. So we know the charge on one of these plates. The number of electrons is simply the charge on one of these plates divided by the charge of one electron. Well, if we look up in our data sheet, the charge on one electron is 1.60 times 10 to the minus 19. If we do the total charge divided by the charge of one electron, gives us 4.4 times 10 to the 10, so therefore the answer is C. So that's questions number 40 and number 41 of the electric fields and the capacitors homework booklet.